Okay, hi 3Us. We're going to do a short little lesson in this video, just reviewing the states of matter, the kinetic molecular theory, and just introduction to um, properties of gases, including pressure, and that will lead us into the gas laws for the next section. So this is a review. Uh, the description of the states of matter is shown in this table here. There are theoretical descriptions as well as observational or empirical descriptions, things that we can't necessarily see, but we infer from just how particles that we can see behave. We can see particles vibrating, moving back and forth. Sometimes in a case of, say, a spring or a pendulum, we can see particles twisting around like a child playing on a swing and twisting around the axis of rotation. We can see objects translating, moving from place to place. So we have different forms of molecular motion as well that we have as a theoretical description. We have properties that we definitely can observe. For solids, we tend to see solids having definite shape and volume. Think of an ice cube. Really hard to compress them. They tend to shatter more when we try to put pressure on them. They don't flow readily, usually solids, unless it's state or form is maybe a special case like a powder. Liquids, on the other hand, like gases, tend to assume the shape of a container. They have a definite volume that can be measured. They're very hard to compress, but both liquids and gases do flow readily. And so these properties here can be explained using the kinetic molecular theory, which for just the types of motion, it's an indication of the strength of attraction between particles. If particles have very strong attraction for one another, we would expect that they would be very close together. They would not be able to translate very much, nor would they be able to rotate. It'd be a little bit like trying to break up the coil on a mattress. They're very rigidly held together in a network. So vibrational motion is the only type of motion that's possible for solids. Liquids have vibrational and rotational, but the particles tend to stay closer together than a solid, or rather further apart than a solid, but they can still move around. So that's the one difference. And in gases, the predominant motion is translational. They may be vibrating a little bit on their own axis, or they may be rotating a little bit around their axis, similar to how the Earth rotates. However, the dominant motion for gases is translational. And we have evidence for that just in the diffusion of gases. A bottle of perfume opened in one corner of a room can be smelled in the opposite corner very quickly, telling us that the particles are moving long distances. They're translating. So these are the properties we have for the three states of matter. And for solids, in your textbook, you'll read about the different classes or categories of solids. We have ionic crystals. We've looked at those before. We have metallic crystals, which for the most part are solids at room temperature. Mercury would be the exception. We have molecular elements and molecular compounds. There's examples of those we've come across before, and all four of those categories of chemical substances can be solids at room temperature because of the strong inter particle forces. They could be ionic or intermolecular. But there's strong forces between solids. The forces between liquid particles tend to be a little bit weaker, and then the weakest of all would be the forces between gases. And all these properties can be explained using intermolecular forces. So the first point here for the kinetic molecular theory has been mentioned already, the three types of forms of motion. We assume that all matter is always moving and moving constantly and randomly. Randomly in that one particle might be doing one type of motion, but another particle could be doing a totally different type of motion. And it's very difficult to predict the location of a given particle because of the interactions with other particles and collisions with walls and container edges. So the Motion of particles is assumed to be constant and random. Collisions of particles with each other, or more specifically with the container walls, is what we call pressure. So a pressure is caused by collisions of particles. And it's, in a physical sense, it's defined as a force per unit area, which means that the higher the force, which is caused by the collisions, the higher the pressure. The smaller the area exposed for collisions, also the larger the pressure. We can think about someone walking in high heels. It's caused in that case by the force of gravity pulling down on the individual. However, the area of contact between the heel and the floor is very small, so that also leads to tremendous pressure on that point of contact. Okay, pressure will become one of the really important properties that we examine in the gas laws. We'll come back to that in section 2 of chapter 9. So the third point we want to make here is that the state of matter is almost entirely determined by the strength of the intermolecular forces. And at room temperature, whether it be a solid, liquid, or a gas, the attraction between particles is going to determine whether or not they have only vibrational motion or whether they have primarily translational motion. So that would be one of the assigned questions for you to be able to explain the trend there. Other properties which can be explained by intermolecular forces would be density, ability to flow, diffuse, ability to be compressed, as well as shape. And the low intermolecular forces of gases in particular explain all of these properties. Finally, under the heading KMT and ideal gases, what an ideal gas really is: one in which gas particles are assumed to have no intermolecular forces, no reaction with one another, and they move in straight lines. The ideal gas properties seem a little bit strange and unrealistic, but when we look at the ideal gas law, this is a simple formula which assumes these facts that gas particles behave a little bit like billiard balls. They don't interact with each other at all, aside from simple collisions, meaning they don't cause each other to veer away or towards another. Let's have a look at just a closing video clip here, just to kind of get you thinking about some of the relationships that we're going to explore in the next section.
A bicycle pump forces air into the confined space of the tire. As more air is added to the tire, the pressure increases. The tire's volume increases slightly, and the air becomes warmer. These observations are predictable properties of gases, and, as we explore in this chapter, they are described by the gas laws.
All right, that concludes this short introductory lesson. We're going to be working on some questions in class tomorrow, and then this will transition right into a package of handouts where you're going to be working kind of independently on the gas laws for section 9.2. So there will be no follow-up lesson for the next section in the textbook for now. You'll just finish these questions in class, and then you'll be doing some work with the graphing calculators and some look at considering different scenarios, and you'll have a chance also to do some little lab demonstrations to help you understand how pressure, volume, and temperature are related for gases. We'll see you tomorrow.